Contingency tables. This is also known as the test for independence for multiple variables. Let's look at an example. The table below summarizes the challenges made by tennis players in the first U.S. Open that used Hawkeye electronic instant replay system. Use a 0.05 significance level to test the claim that success in challenges is independent of gender of the player. Does either gender appear to be more or less successful? So here we have a table of men and women in the rows, and were their challenges successful or not in the columns. So 201 men were successful in their challenges, and 288 men were not successful. And 126 women were successful in their challenges, and 224 were not successful in their challenges. This is a contingency table. It's a two-way frequency table in which the frequencies correspond to two variables, men and women, and then yeses and nos. We're going to test these two variables for independence of one another. Is the dependence of the success based on gender? In this section, the null hypothesis will always be that the row and column variables are independent of one another. Okay, let me show you how to do this. Step 1, state the claim. The success in challenges is independent of gender. That was the claim. After we state the claim, we always state the opposite. How successful a person is in challenges depends on their gender. Then we identify the null hypothesis. The null hypothesis is that the two variables are independent of each other. Now, step 4 is always finding the test statistic. We're going to use exactly the same test statistic, chi-squared, as we did in the previous section. So remember that formula for chi-squared was the sum of the observed minus the expected values squared divided by the expected value for each variable. Now the observed values are given to us in the table, the 201 successful men and the 126 successful women and so on. I want to show you how to find the expected frequencies of each cell, or E. So here's how we're going to do this. In the table on the bottom, we're going to record the expected frequencies. So if we start with the first, couple things to add up, I'm going to add up the 327 is the total yeses. So 201 men yeses plus 126 women yeses gives us 327. And the total for the second column, the no's, 288 plus 224 is 512. I'm going to do the same thing for the columns. The rows. Add up the row totals. So 201 plus 288 in the men row gives us 489. And 126 plus 224 in the women row gives us 350. So we need for each of these rows and each of these columns, we need the total for the row and the total for the column. We also need the grand total. So the 839 you see, you can calculate it one of two ways. You can do 489 plus 350. So the row 1 total plus the row 2 total is 839. You could also have done the column 1 total plus the column 2 total. 327 plus 512 also gives us 839. That 839 is what we call the grand total, and it will be in the denominator of our expected values. So here's how we find each expected value. For each cell, say row 1, column 1, we do the row total that cell is in, multiplied by the column total that cell is in, divided by the grand total. So let's say we're looking at the cell that is for the men row and the yes column. Well, that is the top cell in the left column. So first of all, the row total for the upper left hand would be 201 plus 288, which we already found out is 489. The column total for column 1 would be 201 plus 126, which we already found out is 327. So since that first upper left cell is in row 1, column 1, we're going to multiply those totals together. 489 times 327 for row 1 and column 1, and divide it by the grand total, 839. And our first expected value for the men in the yeses would be 190.59. Okay, let's do the rest of them. Let's move to the men in the no column. So up on our contingency table, that's the cell that has 288. So we need to do row total times column total for row 1, column 2. Row 1's total is 489, just like the first one. Column 2's total, however, is 512 for column 2. And then the grand total is 839. So when we calculate that, we get an expected value for the men in the no's to be 298.41. Okay, let's figure out our expected values for the women. So for the women in the yes column, this is row 2, column 1. That's where the 126 is in our contingency table. So 126 plus 224 gives us a row total of 350 times the 327 from that column total over, again, the 839. So we get 136.41 for the expected value of women yeses. And then finally, the very last cell, women no's, that's in row 2, column 2. So for row 2's grand total, we have 350. For column 2's total, 512. And again, the grand total is 839. So 213.59. Okay, this is the E we're going to use in our same formula for chi-squared test statistic. So I'm going to copy this chart of expected values on the next slide. So here we go. So scooching that up, we have our observed frequencies are all listed. That's the 201, 288, 126, and 224 going along row 1 and then along row 2. And the corresponding expected frequencies, 190.59, 298.41, 136.41, and finally 213.59. Okay, so now we need to subtract the O minus the E for each cell. So a little more room here. So 201 minus 190.59 gives us 10.41. And again, don't worry too much about sign, positive or negative. We're going to square that value anyway. What's interesting about this is we get negative 10.41 for 288 minus 298.41. We get negative 10.41 for the third row and positive 10.41 for the last row. That's just a coincidence. When we square them, it makes calculations a little easier for us. We're going to get 108.3681 for each one of those. However, the final column on the right, they each have different expected values E. 190.59 and 298.41. So this final column will have different values. So 108.3681 divided by 190.59 gives us 0.5686. And 108.3681 divided by its expected value, 298.41, gives us 0.3632. And so on. 108.3681 divided by 136.41 is 0.7944. And finally 0.5074 for the last one. Now remember, when we're calculating chi-squared test statistic, after we find all of those observed minus expected squared divided by expected, we add them up. We add all of those values in the final column up, we get 2.234. Okay, so our chi-squared test statistic is 2.234. Now I'm going to use the critical value method, so I'm going to find the critical value that corresponds to our significance level, which was 0.05% at the beginning. So what we need to know for the contingency table is how you find degrees of freedom. This is a unique degrees of freedom. We're still subtracting 1, but we're going to do rows, the number of rows minus 1, so that'd be 2 minus 1, multiplied by the number of columns minus 1, so times 2 minus 1. So our degrees of freedom is very small. We get 1 degree of freedom. Going to either your chi-squared distribution table and looking up degree freedom 1 for that top row and the 0.05 significance level, we should come up with a critical value of 3.841. Well, since our test statistic was smaller, we're not in the critical region. Remember, these are always right-tailed tests for chi-squared. Since our test statistic was only 2.234, we're not in the critical region, so we fail to reject the null hypothesis. The null hypothesis was that challenges are independent of gender. That was the claim. So our data